Section 1.2b, reviewing what we talked about in the appendix section. 2 times up until now that we have possible domain restrictions in a relation. If we have a variable in the denominator of a fraction, we know that that creates a possible restriction because we know the denominator cannot equal 0. So what do? If we have a variable underneath and we want to know, we take the denominator, we set it equal to 0, and those solutions become the excluded values of the domain. In other words, those are the only values that x cannot be in that function. Variable underneath an even indexed radical can cause an issue because we know that we cannot take the square root or even any indexed radical of a negative number. So we take what's underneath the radical. Since it cannot be negative, that means it can be greater than or equal to 0. And the solution to that inequality tells us exactly what the domain is. Those are the only values that x can be in that relation. So looking at some examples here, state the domain of the function using interval notation. So we're looking for one of two things. You should be asking yourself the question, does this function have a variable underneath an even indexed radical? Does this function have a variable in the denominator of a fraction? If it does not have either one of those two things, we do not have any domain restriction, which means x can be anything. In interval notation, the way that we say x can be anything, it's the interval from negative infinity to infinity. Letter B. Here we do have the possibility of a domain restriction. We have a variable down in the bottom. Take that denominator, set it equal to 0. We know x cannot be negative 2. X can be anything else but negative 2. Well, here's when x can be anything, negative infinity to infinity. When x can be anything but negative 2, we're still going to start at negative infinity, but now we need to go up to negative 2, not include it, union it with the interval that begins right away again at negative 2 and goes out to infinity. So basically we've taken negative infinity to infinity and pulled out negative 2 because we know that x cannot equal that value. Letter C, another possible restriction because this time we do have a variable inside an even indexed radical. So I take the stuff underneath the radical, and we know that it has to be greater than or equal to 0. Solve this inequality. Divide by negative 1. Remember, flips the inequality symbol, so x has to be less than or equal to positive 5. So our domain then is the interval x less than or equal to negative 5. How far left is this going to go? To negative infinity. How far right does it go? To positive 5, and that is included, so we have a bracket. Number 6. It's really a review of what we did yesterday with function notation. F of x is equal to x squared plus x minus 1. So there's our function. We want to find f of x plus h, subtract f of x, and divide the whole thing by h. This will be one of the most missed problems on the Chapter 1 test when there will be one similar to this on the test. And many of you are going to get this wrong, so make sure you know how to do this problem because it will be one just like this on the test. Here's the function we are beginning with. In that function, I need to find f of x plus h. Well, if I just wanted to find that first, f of x plus h means that I need to take x plus h and put it in every single spot that I have x in our function. Once I have that, then I need to subtract from that f of x. Well, what's f of x equal to? Well, f of x is x squared plus x minus 1. And then we are going to divide that whole thing by h. That's it. So I need to take this f of x plus h right here, subtract that, and divide it all by h. So let's go ahead and do that. As I do that, I'm going to begin foiling this out. So we have x squared plus 2xh. Do this in the same color here. X squared plus 2xh plus h squared plus x plus h minus 1. Now I need to subtract off f of x, the whole thing. Since I'm subtracting the whole thing, you must put this in parentheses. If you don't, you're going to get this wrong every time. You're subtracting off the entire function f of x, and now you are dividing this whole thing by h. Once you do this, it's just a matter of simplifying everything correctly. X squared minus x squared is gone. 2xh, nothing to combine that with, so I still have 2xh. H squared. X minus x is gone. Plus h, negative 1 plus 1 is gone. It's all still divided by h. Now I can take an h out of everything, and we're left with 2x plus h plus 1. So individually, not a difficult problem. Everybody should be able to find f of x plus h. Okay? The key things is you're not going to FOIL this out correctly, or you're going to forget to not subtract off this entire term and distribute that negative to each term of f of x, and that's going to cause you to make an error. Last one here. The number n in billions of miles traveled by vans, pickup trucks, and sport utility vehicles in the United States from 1990 to 2000 can be approximated by that model, where t represents the year, with t equals 0 corresponding to 1990. And when you're doing these problems, make sure you are paying attention to how the variables are defined. Use the table feature of a graphing utility to approximate the number of miles traveled by vans, pickup trucks, and sport utility vehicles for each year from 1990 to 2000. Okay, let's look at our equation here first. First, we're dealing with a piecewise function. We know t equals 0 corresponds to 1990. So this domain restriction here that says t has to be between 0 and 4 is really talking about the years 1990 through 1994. This domain restriction on the second piece of our function, t has to be between 5 and 10, is from 1995 to the year 2000. So now we need to find the number of miles traveled by vans, pickup trucks, and sport utilities for each year from 1990 to 2000. Okay, we're going to do that on your calculator. So let's go to the calculator. Put in these two functions. Y equals negative 9.2 x squared plus 84.5 plus 575. Second one, 26.8x plus 657. Hit graph. There's my standard viewing window, and you can see that that's not a good window for this graph. So let's think about this here. In our window, what do the x values represent? Well, it represents the time with t equals 0 corresponding to 1990. So let's just go from 0 up to 12. That would take us through 2002. Our y value is the number of miles traveled. Okay, so how many miles are going to be traveled? And the units are, actually, let's just go zoom fit here and see what the calculator gives us first, and then we'll go back to our window. Zoom fit is zoom and 0 for most of you, depending on the software you're running. Now we can see a little bit better picture of our graph, and actually that's probably about all we need to do. Let's check our window here. Okay, we obviously don't need y to go down to negative values. Let's go up to 1,000 here, just to make it nice numbers, and let's have our scale so that we have nice numbers go up by 100ths. All right, there now is a good graph. We can see our parabola, which is the first piece, and our line, which is the second piece. From 1990 to 1994, we're going to talk about our first piece. From 95 to 2000, we're going to talk about our second piece. So now if we go to our table, we have two different y columns. Remember, for our first values, we're going to be using these first columns right here. So this is 1990, 91, 92, 93, and 94. So once we get to x equals 4, now we're going to switch to y2, and we're going to begin using those values there. Let me make sure I plug this in right here. Negative 9.2x squared plus 84.5. I forgot my x. That's why that picture doesn't quite look right. So let's go ahead and edit this. I'm going to insert an x in there, and now let's look at this graph again. And there we have a little bit better graph. Now if we go back to our table, you can see this, and again through 1994 we're going to be using y1. Once we get to 95, we're going to start using y2. You can arrow down to get those other values through the year 2000. Okay, I'm going to go back up to the beginning here. 1990, 575, and notice the units that we were talking about here were number of miles in billions. So this represents 575 billion. Let's go ahead and record each one of these. So in 1990, 575 billion. 650.3 billion. 707.2 billion. 745.7 billion. In 1994, 765.8 billion. Now we're going to skip over to Y2 because now our domain is for 1995 is in the second piece, and record each one of those. We have 791 billion. 817.8, 844.6, 871.4, 898.2, and 925 billion. So make sure you're paying attention to how variables are defined. Make sure you can change viewing windows so that you can get a good picture of the graphs so you can get the information that you are looking for.